So the talk of today is about on the added value of an ensemble approach at small scales. We will talk about the introduction to the Cosmology systems. And this is a nice slide. Okay, we'll try a little bit to talk about the motivation for why do we need ensemble prediction system also at small scales, and we will talk about the operational implementation of the systems. Basically, the main feature and the main products that we have from Cosmolabs. Then we'll talk a little bit about the statistical evaluation, about some time series evaluation of the products versus CNOP reports. Then we'll talk about a comparison between Cosmolabs and ECNWF EPS using a high resolution network. And then we'll show the impact of using raw versus calibrated Cosmolabs forecast. At the end, we'll talk a little bit about the products that are available on Cosmolabs on the web. Stop me anytime you like. The audience is very different because there are professional forecasters and students. So it's very likely that I may not be clear in some aspects. So interrupting in English, in Italian, in France, in French, in any language you like, but as soon as something's not clear, stop. There is no problem to repeat and try to clarify. It's always a pleasure to speak. So, very quickly, because this was supposed to be the topic of the talk by Chiara, I have just 2 slides on the motivation, which leads to the need for limited error ensemble prediction. As we have seen in these days, we've seen that global ensemble systems are a very valuable tool to try to tackle the problem of predictability, maybe not in a very early range, but say beyond day 2. The issue is that very often ensemble prediction systems are run at a coarser resolution with respect to deterministic or high resolution global predictions. So, to some extent, global ensemble system can have some limitation in skill as regards the forecast of intense and localized weather events, and still nowadays is limited. ECNWF EPS, which has a global ensemble system with the highest resolution in the world, runs at about 32 kilometers of horizontal resolution, which is half of the resolution of the deterministic system. So 32 kilometers can be enough for some for the prediction, or sometimes of weather events, and maybe not enough for other types. And so, in particular, we can see that the limitation in the forecast skill is also due to the fact that there is a low degree of predictability in when we go to very short scale or very short time ranges for this type of severe and localized weather events. We will see that the fish, the length of the forecast horizon will be much shorter today with respect to yesterday. Will be much shorter, unfortunately. So for this reason, we will see that the probabilistic we can say that the probabilistic approach is also required for short range, also at high resolution. So what did we develop at ARPA-C? We developed this Cosmolabs system, which is a mixture of 2 acronyms. LAB stands for Limited Error Ensemble Prediction System, and Cosmo stands for Consortium for Small-Scale Modeling. It's a consortium between national weather services, which includes Germany, Greece, Italy, Poland, Romania, Russia, and Switzerland. Israel may enter in 1 year or 2. And it is a consortium. It is one of the 3-4 big consortia which are in Europe. The other is Ireland, then there is UK Metophy, which is a bit on its own, and then the Aladdin Consortium and LACE. So there are just a few consortia in Europe of national weather services, and Cosmo is one of that. The motivation for the development of this system was basically the idea, how can we try to combine the advantages of global model ensembles, which have many members, which provide a set of different weather scenarios, with the high resolution details, which are needed to identify the occurrence of high impact and localized weather events like heavy rainfall, strong winds, temperature anomalies, snowfalls, cold temperature over cities, and this type of events. So the idea was try to generate Cosmolabs just to improve the forecast of high impact events in short and early medium range. They up to day 5. At the moment, the forecast range is up to 132 hours. So it's an ensemble system targeted for the short range, but with some extension towards the medium range. So what happens when you have a limited area model and you start from a global model? What you do, you have a global ensemble, which can be CNWF, but can be any type of global ensemble, which has many members. You nest, so you give the global model members, give you the initial and boundary condition, you do the nesting, and you have a number of limited area ensemble forecasts. This is so-called total downscaling, which if you have 10 members here, you have 10 members here. If you have 25 members here, you have 25 members here. If you have 50 members here, you have 50 members here. Total downscale. You try to downscale at local scale the information given by the global model ensemble. This is called total downscaling or brute force approach, in which you try to downscale all the information you can. This is not always possible because of computer time limitation. And what we tried to develop in Bologna was the following. You have still the global ensemble, which many members, which can be 50, for example, for CNWF EPS. You perform first an intermediate step in which you have an ensemble size reduction. It is like to have a lemon and just squeeze a lemon, try to get the juice out of it. So in which you basically try to condense the most important information in terms of weather patterns. And then with this, here we start with many rows, with many black arrows. Here we are left with fewer black arrows, which are used for the nesting with the limited area model. This is the approach we had, in which, starting from many global ensemble systems, members, which are the many arrows here, you are left with only representative members, which are the members which are the key information of the global ensemble system. At least this is what we hope. And try to be a bit more in a graphical way. We can imagine that these are a set of initial conditions from a global model, which after some time evolve in different possible evolution scenarios. You can see we have 6 points here, 1 here, and 5 here. What we do is that we reduce the ensemble size in this way. We make a cluster analysis. This green over yellow-green is not very clear, but anyway, we try to select for each type of group a member which is representative of the weather scenario. So we divide the member in clusters, in groups which are similar. So we select only the yellow members. So for many black lines, I'm left with only 3 yellow lines, and these yellow lines are the ones which drive the limited area model ensemble. In this way, we don't have anymore many black lines. We have only 3 yellow lines, which drive the limited area model integration, which are the red lines in the figure. This is just the heart of the methodology we use for Cosmolabs, and try to go a bit more in detail. This is the slide that we try to describe now. We run the system in which we group together 2 successive runs of CNWF EPS. If something is not clear in this picture, ask, because it has many features, and I may forget something or I may misrepresent something. So I have 2 successive runs of CNWF EPS. One started at 0Z and started at 12Z. After 4 days, I construct the groups. So I have 51 members here, 51 members here. So I have here on aggregate 102 members. And I construct 16 groups on the basis of a number of variables. I look how similar are the fields in terms of geopotential, U, V, specific humidity in the mid-lower troposphere at 500, 700, 850 hectopascal. I look at how similar they are at 2 time steps, so over a trajectory between day 4 and day 5. And I look at how similar they are over the European area, which is the red rectangle of the figure here. So over this area here, the red rectangle, I look how similar the the different members are, or how similar, or how different are, and then I make groups of I construct 16 groups. Why 16? Because it's a matter of try to have, it's important that an ensemble system has always the same number of members. Because both for a practical reason, because you have, so you always know how much computer time you will use. Any problem?
No, it's
Okay, okay, I can try to use this. Okay, I go on. So we can try to say that from the 102 members, I select the 16 members, which are the representative members, which drive a limited error model integration. In this way, I start from 102 members. I'm left with 16 members, which drive the Cosmology integration. The Cosmology integration are run over this blue domain, this one, which is center of the Central and Southern Europe. So in this way, twice a day, starting 0 and 12, so this system runs twice a day, I have a 5-day forecast at high resolution over Europe. The system runs at 7 kilometers of horizontal resolution, 40 model levels, 5.5 days of forecast range. The suite, all the system runs at TCWF, and it is managed from Bologna as a time-critical application, which means it has a high priority with respect to other jobs, and so that the products can run quickly and can be delivered quickly to the Cosmo countries. Other things which are important are the 16-member runs with 2 different convection schemes. Members 1 to 8 run with a TIDK convection scheme. Member 9 to 16 run with IFS vector convection scheme. Then we apply some perturbation in turbulence scheme and physical parameterization, and we take the solid initial condition from Cosmo U, which is another Cosmo system run by DVD, by the German Weather Service. If this is all clear, you are already very...
Andrea?
Yes?
Which you wrote that you use 2 time steps
Yeah.
in order to select the times for
Clustering.
Which time steps are they?
Day 4 and day 5, plus 96 plus 120. It is quite late in the range because initially the idea was we want the global ensemble to have already a lot of spread, or quite to have the different members to have already to have time to differentiate one from the other, so to have time to highlight a different weather scenario. This is a very, very old decision of 10 years ago, something like that. And we are revising in this month if it is probably better to shift the window a bit earlier in the forecast range. But at the moment, it is still between day 4 and day 5, where we go and look how similar or how different are the ECNBF members.
And do you still think it is convenient to use also younger and older? Yes.
This is somehow a strategic choice, which we can, or I can say now, it is a way in which you have, it's a compromise. You sacrifice a little bit of skill because you will nest the model on some older forecast, but you have a bit more spread, and your system is less jumpy because you have members from the older and the younger. So it has less jumpiness. So this is a compromise. It is not a perfect idea, but it's not an operational compromise between skill and spread and consistency. Fabrizio?
I don't know if I understood well, but when you choose the members, it seems that you choose a number of elements which maintain the most variability there is in all the...
Yes, yes, it's more or less correct. Yes.
When you choose the yellow, don't you think that you lost some information? That is that the same yellow has the same weight of others, but in that example, the yellow one it really have more weight than the other because there is a lot of members in the yellow.
This yellow is more important than this yellow. Okay. I didn't say.
That you lose some information.
I didn't say this. It is weighted. Okay, yeah, okay. Each member is weighted according to the cluster population, which means that when then you construct the product, the probabilities or the meteograms, we attach a weight which has a memory of this cluster size. You're right, I forgot to say that actually we try to keep memory of how the different clusters were populated. So you attach a heavier weight to the member which came from a highly populated cluster. In this way, we hope that this information also transfer to the limited error runs. Yeah.
So if your members, your EPS members, have used different convection, or they have some perturbations on physics or something like that, it means that the further EPS is different from a standard EPS. Is an EPS run just for you?
No, this is the operational EPS. These are the one that Roberto Buizza said yesterday.
Okay.
No, the normal EPS, 0Z and 12Z.
And what is using either TIC or QC?
It is in Cosmo runs.
Okay.
In Cosmo, we use two different convection schemes. No, in the global model is as it is. They don't do anything special for us. They just save the fields at model level for one day. They did because normally EPS did not produce model level fields. There was a big thing that ECMF did not produce model level field for EPS. They produced model level field only for the deterministic. The novelty was to produce model level fields. So that in real time, we grab the fields, we do the interpolation, and we can run the model. They don't store anything, they just produce the field and keep for a day, 1.5. Okay, so there are different types of perturbation, but probably is not very relevant. So what do we produce? We produce a core products, which are the 16 Cosmo model runs, which takes initial and 3-hourly boundary condition from the 16 selected members, which are used to generate via weights, the weight we were saying before, the weights which are, is something clear? No, just say no. If just to generate the probabilistic output, which means with other product that we will see later on. We start at 0Z and 12, and the forecast range is 132 hours. In addition to that, we also have one deterministic run, or Roberto would say one single run, which is nested on the high resolution ECMF forecast. This is basically is not a run which enter the probability products. It is a sort of run which helps us to understand when the ensemble and the deterministic go for two different ways, goes for two different solutions. And it has in a way the same feature as the operational run, and it runs twice a day. So not only 12 as is written here, but 0 and 12. And then there is also this is not in real time, it is a proxy run in which we run the model nested on analysis, just to have a sort of downscale ECMF analysis, just to have a sort of reference run which you use then for verification. So what are mainly the real-time products are basically probability product, 24-hour rainfall, precipitation exceeding number of threshold, precipitation over 3 days exceeding threshold, snowfall exceeding number of threshold as well, wind gust, this is wind gust exceeding number of threshold, maximum minimum temperature, 0 degree isotherms below some threshold, the Cape above some threshold, the Showalter index, which is an instability index below some threshold, and then you have also the meteograms, which are over a number of station points in terms of temperature, precipitation, wind speed, cloud cover, and other things. And also you can have the maps like probabilities of precipitation about 1 millimeter or a number of meteographs. But this is in a way a product that we'll see later on in today. So the products go to the national regional services, go to Germany, to Switzerland, to Greece, to Romania, to Rome, to Bologna, Alpa Piemonte, Alpa Veneto, Bolzano, Meteo Trentino. I may have forgotten, I think Alpa Friuli Giulia, Alpa Lombardia, international organization, private companies. I hope I didn't, and some products actually, and some regional services also look at the products that are displayed on our web pages. I may have forgotten some regions, but I hope not. And so now we have a look a little bit of some features and some features of the system and some problems which are related to this. For example, we decided to take the soil initial condition from Cosmo. So we have a sort of lobotomy system. We have a Frankenstein system, which means we have the upper level fields from ECMWF, but we take the soil not from ECMWF. Why did we do this? Why this choice? This is a picture we got from Meteo Suisse, from Andrea Walzer, from Meteo Suisse, which shows the snow height interpolated from IFS, from the global model system ECMWF. We can see that there are the interpolation acting in such a way that the valleys are filled by snow. This is the problem of the interpolation, but it is a problem due to the jump in resolution from the global model to the limited error model. You can see this unrealistic red 2.5 meter of snow height in some valleys, Switzerland and over Italy. And the idea was basically how can we try to get rid of this problem? We tried to make a test in which on the left was the old system in which we take the initial condition from ECMWF EPS members. In other ensembles, so we ran two ensembles of the same size for a few months in which we were taking the upper level fields were still from ECMWF EPS members. But the soil was taken from Cosmo U, which is a Cosmo model run by DVD, which has the same grid points. In this way, they were not in particular in interpolation. We were taking the soil humidity, the soil wetness, the density of snow, the temperature of snow, the amount of fresh snow. Anyway, a number of surface and soil layer fields in order to try to assess the impact of using a higher resolution initialization of the soil. We ran the system for about 100 days, from December 2010 up to March 2011, so some years ago. And now here we have some results. So here on the x-axis I have the forecast length. On the y-axis I have the bias in Kelvin. This is the bias of 2 meter temperature ensemble mean. The red line, there are two lines. The red is always the operational system, and the black is always the new system, the one which is under test. This is a verification done over the synop reports, which are in the domain, which are about 1,400. What we can, and here we have 3 plots. Here are the stations which are over the full domain, the one we saw before, the larger one, Central Southern Europe. This is a sort of alpine domain, and this is a sort of station which low altitude, just 100 station, basically in the Po Valley and along the coast. So always on the x-axis forecast length, y-axis the bias. In any case, we can say that the bias should be closer. Its bias is somehow a sign of the systematic error of the system. If it is above 0, it is too warm. If it is below 0, it's too cold. The forecast is too cold. What we can see here that the red line, the black line, is generally is closer to 0 for the test ensemble. And also the amplitude of the diurnal cycle is smaller. What we can see here is we tend to have the run start at 12, so here we are in the afternoon, here midnight, and here we are at midday again. So I tend to have a a warmer, close to zero bias at about lunchtime, and a colder bias in the afternoon, evening. And this seems to carry on throughout all the forecast length. Here the verification is limited to 2 days, but we can see that in the 3 cases, the improvement is systematic in the sense that you don't remove the bias, you reduce it, okay? The cold bias is a bit reduced, and also the amplitude of the bias is a bit smaller. We can say that it is not, we didn't solve the problem of the bias of the model, but at least we tried to reduce it to some extent. This is for temperature. This is the plot before was for the bias, or the systematic error. Here it is a mean absolute error. What we did is on the x-axis, again, the forecast length. On the y-axis, the mean absolute value in the mean absolute error in Kelvin. And we can see here that, and the error, the lower the better. In this case, we can see all the 3 domains, or the full domain, the alpine domain, and the Po Valley coastal domain. We can see that, especially in these 2 domains, the black line is below the red lines, which means that the new system has lower error. We can see that this is especially true for daytime verification, especially at lunchtime. When you verify the ensemble at lunchtime, the ensemble mean at lunchtime, you can see that the gap is a bit larger. So again, you did not make, you did not remove the error, but at least you have a reduction of that. Similar story for the, if you look no more at temperature, but dew point temperature, which is temperatura di rugiada in Italian. And again, on the x-axis I have the forecast length, on the y-axis I have the bias. And we can see that here maybe the impact is less dramatic than before. We can see that we have a slightly closer to 0 for the black line with comparison to the red, but we can say that is small the impact, but seems to go, especially in the alpine area, in the right direction. And especially at low level, we had a problem with a dry bias, which you can see here, the red line was below 0, which means dry bias of the model, all the ensemble members, and here it seems to be a bit reduced for all the forecast ranges. So we skip this while we don't finish anymore. And we also noticed that the impact on precipitation was neutral. So the transfer of the file from DVD to SNBF was solid, was timely, was working fine. And eventually we implemented the system on the 11th of April. And we got from Meteoswiss this fantastic picture, which was, this one is the one which we saw before on the 10th of April, where this situation of the snow interpolated from Eastern Black EPS. And here is the new system, so snow taken at high resolution from Cosmo EU. So from the high resolution, this is basically snow at about 30 kilometers interpolated to a grid of 7 kilometers, which was created this unrealistic snow height. This is a Cosmo at 7 kilometers, which gives the snow and the soil field to another 7 kilometer model. We can see higher resolution details and also more realistic patterns, thanks to the high resolution of the snow analysis. And still from Andrea from Meteoswiss, we noticed we got this interesting verification. This is a verification of temperature of Switzerland for JJA, June, July, August 2010. On the x-axis, I have the forecast rate, I have the time of the day, and on the y-axis, I have the value of temperature in Kelvin. The black lines are the observation, the one I should try to match, and on the red lines are the deterministic system, the Cosmo, which is right, the deterministic mode, like Lamy, basically. It's a close relative of Lamy, the red line. And the blue line is the ensemble mean. This was JJA 2010, so below the change. Below the change, there was a sort of systematic error of 2 Kelvin. We were 2 Kelvin too cold. The ensemble, all the ensemble members were about 2 Kelvin too cold, especially in the afternoon. And the following year, we had a reverse situation. We can see the jump here, okay, just to have an idea. The following year, after the change, we can see that this time the blue line was closer to the observation, which are black. So we can see that cosmolapse ensemble mean was outperforming the deterministic run for all the lead times, which are between day 1 and day 2. So, okay, this may mean that maybe the year 2011 was more predictable, less predictable than the year before. It's not conclusive of maybe anything, but
Andrea,
yeah.
if I have understood this correctly, this is the temperature.
Yeah.
Yes, so it's not a verification, it's a validation.
It's a
shows that
validation.
the system is behaving like the atmosphere.
Yes.
But that doesn't say anything necessarily about the skill of forecasting.
It says that here you are following more faithfully the diurnal cycle.
Fine, but it's not verification, it's validation.
It's validation. Okay. Okay.
Forecast can still be bad.
Sorry.
On average, it's sort of the system is a good simulation of the atmosphere.
Yeah.
Great, fantastic. But it doesn't say about
The score. Either
efficiency. So it's,
there's slide later on which are more.
if I have understood it correctly.
Yeah. Okay. So what we can see here is that okay, we follow more faithfully the diurnal cycle of the observations, and so this is interesting in a way also for forecaster. The ensemble mean can be more faithful than the deterministic run, which is a method we can try to take back home. And this is also, if you do the verification of dew point temperature of the synopsis, so before I was showing temperature, this is dew point temperature, we can say that, we can see against over the Swiss stations, we can say that the ensemble mean has a bias closer to 0 than the deterministic run. The deterministic run runs up to day 3, so that's why the red line, which is the deterministic run, has a line stops earlier than the blue line. On the x-axis I have the forecast range, on the y-axis I have the bias or mean error, and similar thing applied to the standard deviation, which is a measure of error. This time the blue line, which is the error of the ensemble mean, is lower, is below the red line, which is the deterministic Cosmo run by MeteoSwiss. So, also a positive impact also over cloud cover and also for temperature. But we can try now to move to another thing, try to identify the fact that we use 2 different convection schemes. The idea was that, okay, we use 2 different convection schemes because none of them is perfect, they should have a similar performance, but what can happen is that for some cases you have 8 members which will go for a certain weather prediction, and member 9 to 16 will go for a different pattern. We can see that members 1 to 8, again from Andrea Valse from MeteoSwiss, we can see that members 1 to 8 were going for slightly heavier precipitation in the area of Canton Ticino and also some parts in Italy here. This is for a case study of last summer, forecast of 1 day on 23rd of July. We can see here some cases of precipitation about 120 millimeters. And in generally speaking, all the 8 members were going for a quite high precipitation scenario, while the other member were going for a lighter precipitation scenario, which is just a case study with fancy. Simply tells you that the impact of using 2 different convection schemes is not negligible on specific weather events. This time, this one was right, anyway. The 8 members were right. So it rained, anyway, basically. And what we would try to be a bit more, to investigate a bit more this idea. And so we tested, we made some analysis of the performance of 8-member ensemble, the one composed by the TDK convection scheme, and we also checked the performance of member 9 to 16 to see. We look at the period March, April, May of 2014, last spring, which was very rainy, and we compare the full ensemble system, 16 members, the first 8 members, and member 9 to 16, in terms of total precipitation. Okay, not quickly, anyway, just to show you some results. 3 lines on this graph. The red line is a full ensemble system. The blue line is the 8 members with a Bechtel scheme, the one which was not raining in the previous picture. And the green light is the TDK scheme, the one which is operational in a way in deterministic runs. For example, LAMI, or also the system runs by DVD or Meteor Swiss or the other system all use the TDK convection scheme. We can see here that on the x-axis I have the forecast length, on the y-axis I have the value of the score, the rock area value, which has to be high. It is a measure somehow of how the system is able to discriminate between false alarm and heat rates. And this is, for example, how I can predict the event total precipitation larger than 1 millimeter, and here is how I can predict the event total precipitation greater than 10 millimeters. Generally speaking, we can see that, okay, as we could expect, the best performance is given by the full ensemble, the red line, but we can see that also on a statistical basis, on a 3 months verification, the TDK members seem to perform better than the IFS Bechtel members. So this seems to be very clear for some scores, like for example in the RAM probability skill score, the one which was introduced yesterday by Roberto, we can see that the performance of the red line, which is a full ensemble system, is very close to the one given by the green, which are just the 8 members, which there is quite a big jump in skill between the green members and the blue members. This is a cycle in the score, which means this is typical of Cosmo. Unfortunately, we tend to predict better precipitation occurring between the night, between 18Z and 6Z, and we predict less better precipitation occurring between 6 and 18, so daytime precipitation. This is a feature of Cosmo model in many different, when you do this verification against the synop. And so this is work in progress. This is actually a lot of work in progress to try to cure this problem. And so we can go on and try to get also the impact of the members you use, because when you have a limited error model, you can always say, okay, your system improved, but is it because you have a better model or because you receive better initial conditions and boundary conditions? This is a problem which afflicts limited error ensemble, limited error model community. Is it because you are good or because you get good fields from the global system? Some years ago, ECNWF made this update in which they changed, Roberto spoke about it the other day, about the combination of ensemble data assimilation and singular vector perturbation. So quite a big change was in 2010. And they were claiming that this system was limited error ensemble prediction system that use EPS initial conditions will benefit from this improvement. There was statement, brave statement. And we say, okay, but is it, this was written in the newsletter, but is it really true? So did we really get a benefit? So we check the spread skill relation of Cosmology before the improvement and after the improvement. We make a very quick check. We check 2 seasons, which autumn 2009, autumn 2010. So one before the change, one after the change. We look at the verification of temperature at 850 hectopascal. We consider we made verification of Cosmolabs against ECNWF analysis, try to have a quick idea of the impact that could have happened. This is a rank histogram, which is, I think yesterday was shown yesterday. speak to you about the rank histogram? Everybody sleeping or? Talagram, okay, Talagram diagram, okay, Talagram is the same. What basically happens is that this should be very flat. It's not flat anyway, but in any case, a U-shape means that the ensemble is under-dispersive. A non-symmetric U-shape means that you are under-dispersive and you have a bias. So in this way, you have, on the x-axis, you have the classes, which means if you have 16 members, you have 17 classes, because you can have situation when the analysis is below the minimum or above the maximum value, or can be in between. And on the y-axis, you have the frequency. There are two lines. The red line is for 2009, September, October, November 2009, and the black line is for autumn 2010. This is the forecast range 12 hours, so early in the forecast range, and this is a bit later, at day 3. We can say that in any case, we have a cold bias, because we can say that this U-shape is a bit non-symmetric, which means that very often it happens that the analysis stays to the right, which means that all the ensemble members are too cold, because stay to the left. But we can say that the spread, as the situation has slightly improved, in the sense that this big tendency to have many situations where the analysis were warmer is decreased between moving from the red to the black line. So we could see some impact in this score, and also in the reliability diagram, what we could notice that this is looking at, on the x-axis, the forecast probability. On the y-axis, I have the observed frequency. We should try to be as close as possible to the diagonal. And what happens sometimes for upper level fields, it happens that you are above the diagonal, which means that you are underconfident. So you give two low value probabilities with respect to observed frequency. So you predict something with 0.4 probability, but anyway, but actually this event happens more often than you expect. And we can see that for the event of temperature above 0 degrees, which are these two panels, or for the events temperature above 10 degrees Celsius, we can see that the black line, which is 2010, is a bit closer to the diagonal with respect to the red line. This was just a quick check that we did. It is not conclusive, because then for only that year we may check also for the following years, which anyway more or less confirm these results. There was need to study more season, more variable, but we noted that this positive impact of this enabler FEPS was transferred to the limited area model integrations. So now we can try to move to have a look at how you can evaluate statistically this system. We look at the verification against the CNOP on the GTS. We can look at 12-hour accumulated precipitation. We made the verification of a long period. We try to update this every 6 months. We update. So this is verification from December 2002 up to May 2014. We made verification of this alpine domain and also of the full domain. So these are about 470 stations. We look at the performance of the system in terms of 12-hour accumulated precipitation. We look at several forecast ranges between 618, 1830, and so on, up to day 5. We look at several thresholds over a number of scores. And we consider monthly and seasonal scores. So next 3 slides are a bit boring probably, but I hope you don't fall asleep. So what we did is, on the x-axis, I have the month, January 2003, July 2003, up to July 2014. On the y-axis, I have the value of the score, the rock area, which is the area under the heat rate versus the forced rate diagram. The higher, the better. And I have 4 lines on this score, which tells you how the skill of the system improved in terms of 4 events. So the red line tells me, the black line tells me how the skill in terms of how do I predict precipitation above 1 millimeter changing in the years. The red line tells me how the forecast of precipitation evolved in the years in terms of precipitation exceeding 5 millimeters. the green and the blue line, tells me how the precipitation skill, how the skill of the forecast of precipitation about 50 millimeters evolved in the years. We're checking at the forecast step between 30 and 42 hours, so quite early in the forecast range. And here I have put a number of milestones we can call when there were important changes to the system. In June 2004, we increased ensemble size from 5 to 10. In February 2006, we increased ensemble size from 10 to 16, and we increased the model level, the vertical resolution from 32 to 40 model levels. In December 2007, we put the RK stay for Runge-Kutta, so a new numerical scheme. In December 2009, we upgraded the horizontal resolution to 7 kilometers. April 2011 was the one we saw before. We used thermostat analysis from DVD. 2012, we did some tuning to the perturbation. So these are a number of changes, important changes. And we can see that in any case, there is a positive trend in the sense that there are probably different behavior depending on the event you consider. Very often the blue line is a bit far apart from the other lines because you don't have many observations, many events. So when the season is very, very wet, the lines are very close. When the seasons are very, very dry, you can see a jump because there is a bit there is little significance of the result for the 15 millimeter flash. It can be either good or bad, but may not imply a true skill of the system. So here I made a 6 months running mean to have the scores which are a bit more readable. We can see that we have quite good score also especially for the last winter and for spring, and we can see that a positive trend can be identified. Maybe we don't have the situation like ECNWF, which has 1 day per decade in foster skill improvement. But here we are talking about precipitation, not geopotential height at 500 millibars. So this is a dirty word, we could say. So a bit, I don't know, a bit more challenging, I would dare to say. And so we can see that this positive trend is evident, I would say, for the whole thresholds, but you may disagree. And it's also true also if you look at day 4, between 78 and 90 hours. Okay, the numbers are lower, so we can see that if you go from one panel to the other, here the values, now we are above 0.9, while here at day 4 we are a bit below. So we can see that still there is a positive trend at all the different forecast range. And we have some loss of predictability with increased forecast range, as is normal, but it is not incredible. So we were quite happy with its results. And what we also tried to see was also look at different scores. Also, for example, the outliers, which tells you how many times the analysis is outside the forecast interval spanned by the ensemble member. This time I have on the x-axis, I have the month of reference. On the y-axis, I have the percentage of times the analysis is outside. It's something you don't like very much in an ensemble system, that you give many possibilities to your system and all of them are wrong. This is something you try to avoid very often. You try to avoid as much as possible. So it has to be the lower the better, as low as possible. And this time the 4 lines tells you the 4 different forecast ranges, which tells you, for example, the red line tells you how many often the analysis is outside the forecast interval of the ensemble at the forecast range between 30 and 42 hours. The green line tells you between day 2 forecast range, almost day 3 between 54 and 66 hour forecast range, and then the blue and the yellow tells you how often it happens that the analysis is outside for the longer ranges. Again, here we also reported the important steps in Cosmolab's history, and we can say that we can see some seasonal cycle. You can have peaks in winter. You tend to have more outliers in winter. Here you see we are in January, for example, here 2009, January 2010. You can have these peaks in winter, which is when the system is more active. We can say that there was an overall reduction of outliers up to 2007, then up again, and then a limited decrease in the last 1.5 years. So here we're trying to identify a trend to see if something is going on all over the domain. Then locally the score can be very different. We tend to have better skill over Switzerland and Germany and worse skill over Italy, but overall speaking we can see some positive tendency. And also we can also look not only at the time series but also how the skill evolved, for example, in the last 4 winters. Here, again, on the x-axis, I have the forecast lengths. On the y-axis, the percentage of outliers. And here there are 4 lines. The red lines tell you the performance of the system in 2000 and in winter 2010-2011. The black line, they are the winter 2011-2012. The gray line, 2012-2013. And this last line was last winter, 2013-2014. These are the Cosmo model versions. And what we can see here is that last winter was actually quite good. That's why I'm showing the score. And we have the best result for the last winter. And we can say that we tend to go quite stable in the last forecast ranges. So for longer ranges, between day 4 and day 5, we tend to have quite a low number of outliers. But we can say that for short forecast ranges, there was a gain in skill in the last winter. We have to see then, it is clear then the different statistics of each season. We can say that depending on how the season were, well, it was more rainy or less rainy, more dominated by some weather pattern instead of others, can change actually the performance of the system. But if you look at a number of seasons, you can have an idea of how the skill of the system is evolving season by season. Now, I have many scores of this, but this is very boring, so I try to skip a bit, otherwise it's a bit tiring. And I try to look at very quickly, we talk about the operational verification using SYNOP. We can see that this some time series scores show some positive trend with good performance for last winter and some normal score, which I didn't explain in detail, for last spring. Now we can have a look with the intercomparison against ECNW FEPS, because if you enter the business of ensemble forecasting, we have to show that you give some added value to the global system. Otherwise, it's more difficult to justify that you exist. Otherwise, there is no point actually in showing that that you don't do a better job than what is already on the market. So, what we try to make a comparison of Cosmolabs and ECNW FEPS, we use the high resolution network, which is we use a network of non-GTS stations. From December 2009 and May 2014, I am redoing this exercise also with Filiberez Giulia observations. What is, okay, here you are. We are working on that because it is important region because it was the most rainy, so it is very helpful for statistics at high thresholds. And so we use this number of non-GTS stations, which is a very dense network. We could not do it in other regions because we don't have the high resolution network of France, of Austria, or of other regions. And what we did is that when you compare two systems with different horizontal resolution, we have to try to find a decent compromise to make verification. What we basically did was we divided all the interval or all the domain in boxes. We look at the performance in terms of 24-hour precipitation. We compare Cosmolabs, which has 16 members, 7 kilometer, 40 model level, against the full EPS, 51 members, 30 kilometer, 62 model level. So Cosmolabs has fewer members, but higher resolution. This one has more members, but lower resolution. Who wins? So what we see is the performance over boxes, which means that we made these schematics. I divide the system in boxes. Within X boxes, I have the grid points, which are the black dots. And I have several observations. What we did here was, within X box, you can consider the average of precipitation predicted by each model against the average of forecast predicted by each ensemble system. Or you can consider the maximum value of precipitation against the maximum value of observed. So you can have different types of measure of precipitation. You can consider the cumulative volume of water deployed in a region, so you can say the total amount within a region, within a box, so which is average, against the average precipitation, or the rainfall peaks which occur in the same region. So you can lose a little bit of precision in terms of localization. You can say, for me, it's enough that the model is able to capture a peak within a box, and but I may not be interested in the actual location or where the peak occurred. So you can have you can play a bit with this system, with this approach, and to some extent it is a bit more fair to have this type of comparison when you have systems with different horizontal resolution. So what we basically did is that you construct an observation mask, which has 1 degree times 1 degree, and then you look inside each box, average precipitation against average observed, or maximum precipitation against maximum observed. Here I will show you the results of maximum precipitation within a box. For average precipitation, you don't see many impact, but for peaks, prediction of peaks within a box, you can see some impact. So what I'm showing here, on the x-axis I have the rain probability, on the x-axis I have the month of forecast, on the y-axis I have the value of the score, which has to be the higher the better and above 0. So the blue line is Isenberg EPS, and the red line is Cosmolabs. We have to say that in winter the performance is worse because many stations are not heated, and so then you have a problem with melting, that the snow melts the day after, or several days after it has after the precipitation, and especially this winter, as we will see in the case studies later on, was a very snowy winter, and it was possibly related to the presence of snow because some stations are not heated, at least in our region is sure. Yes? Tell me.
Now, one question. If you have 16 members, you take the maximum?
No. For each member, I was not clear. Okay, sorry. For each member, I take the maximum predicted within that box for that member.
The box is the big
Yeah. The maximum for each member, I take in this case I have 36 grid points. I take the maximum, and I look at the maximum of the red crosses for each member of Cosmolabs and Isenberg, and then I make the scores.
Where are they in the following blocks?
Here you mean, or no, earlier? Now here, this is a sort of cumulative scores in which you have, it is a rank probability skill score, which is, it is accumulated over all the thresholds. So it is a score which does not tell you how you went for the 1 millimeter, 5 millimeter, 10 millimeter, but it is a score which tells you it is somehow cumulated for the different thresholds, for between 0 and 1, 1 and 5, 5 and 10, 10 and 25, and so on. So it is not a score for thresholds. So it's a score which tells you how the overall performance of your system is. It's not, you don't see a line per member, but one line for the full ensemble. Federico, you say something?
Yeah, about the comment on the observation, but if
Yes, yes.
Cosmolabs.
Yeah. But you can see that anyway, the performance is worse in winter for both systems in a way.
But the drop there in the first graph is...
Yeah, this is, you should look more here, because the ramp probability score is a score which depends on the ensemble size. So it is not a fair score when you compare two systems with different ensemble size. You should work with this, the bias ramp probability score, which is a score which keeps into account the different ensemble size. So the fairer comparison is the one to the right. So in which you notice that also in the bluff for winters as a drop in skill in the most in snowy winters. And well, in any case, what you can, so we can say that at early, comment? No. In the early years, ECNWF was maybe a bit better than ECNWF. So between 2010, 2011, ECNWF was giving was giving better scores than ECNWF, than Cosmolabs, because the blue line is above, is higher than the red line. In the last years, we can say that maybe since 2013, probably, or something like that, the red line is always above. So we can say that there is actually an added value for the prediction of a 24-hour cumulative precipitation. This is in the short range, between day 1 and day 2. This is in a way confirmed also for other scores and also for other forecast ranges. We can see here, for example, it is the same score, but at day 5. It has the same score. The only thing that changes is day 5. And again, we can see a similar story with ECNWF better in 2010, 2011, and Cosmolabs winning since the beginning of 2013, more or less. So some added value in comparison with ECNWF EPS. And for the rock error, we can go to the number of outliers, which means how many times the analysis is outside the interval spanned by the forecast members. Here I have the lower the better. The red is always Cosmolabs, blue is always ECNWF. This is in the short range. The solid lines are in the short range, and the dashed line are in the longer range. It is normal that as the forecast range increases, the number of outliers decrease, because the ensemble opens, the spread becomes larger and larger, and so it is less likely that the analysis is outside the ensemble members. But in any case, we can say that there is a better performance of Cosmolabs in any case. So, about the intercomparison, we can say there is a higher skill of the ensemble for verification of the boxes. We speak quickly about the calibration. What do? We calibrate individual members, individual Cosmolabs member. We made this exercise. Tommaso is not here, it's a pity. So we made, tell me.
How much do you think you will, because we should have...
This is 3 slides, okay. I finished, yeah. I wanted a coffee as well. Yeah, and so the idea was try to make, we make this calibrated precipitation over Germany, Switzerland, and Emilia-Romagna. Why this region? Because are the regions which gave us a number of observations from 1971 up to now. It's always difficult to collect observations everywhere. It's easier actually to collect observations out in Germany and Switzerland than in some regions of Italy. Unfortunately, this has to be said. And so what we made verification was to try to compare the raw forecast with the calibrated forecast. I don't speak about the calibration method because I think it was already described in the previous talks. And this I don't say. Basically what we try to show is that for spring 2013, we made this we did different tests. We look on the x-axis the forecast length, on the y-axis the rank probability skill score, which has to be the higher the better. I'm looking only at Cosmolabs. Cosmolabs row without any correction is the red line, and the always correction is the blue line. In this case, you can see some impact, some positive impact, and also in terms of reliability. So the forecast probability on the x-axis and the observed frequency on the y-axis. You can see again that on the operational one, which is the red one, is overconfident, which means I have too high probabilities. I am below the diagonal, which means sometimes I predict something which happens 60%, but actually this event happens 40% of the time. So I am overconfident, I give too much probability to an event, and which happens less frequently. While if I use with calibration, I have much closer to the diagonal. And the event I was considering was 10 millimeter of 24 hours between in this forecast interval. So to some extent, we can say that these are other scores which say anyway say similar things. Basically, the number of outliers, and this is looking at all the stations in Switzerland, Germany, and Italy, and only over Italy, over the Emilia-Romagna area, which means that there is a stronger impact over the Emilia-Romagna region than over the Swiss and Germany stations. This has to do with the fact that the model performs better over Switzerland, Germany, and less good over Italy. So there is a larger margin of improvement over Italy. That's why the calibration gives you added value. And I think this is also a positive impact of the calibration. And I think we can stop here because we're just at a moment of the products on the web. And thank you for your attention. So now we are at the point of trying to see what is available on the web in terms of probabilistic product, and we give a look at a little bit of some probabilistic products which are available online on the web at our web as a service, and some of them are very general and very traditional. Others are a bit more rather than complicated, there is some more subtle. So this is quite very traditional, which is a typical probability map with the precipitation of snowfall above a number of thresholds, 1, 5, 10, and 20. This is for the case of 30th of January this year. But this is quite simple. If there is something unclear, stop immediately and ask. Where the colors tells you the level probabilities, 10, 30% green, 30 to 60 blue, 30 to 90 purple, and above 90 red. Just to give you an idea of the probability of snowfall for different thresholds. And then there are, this is quite standard, I would say, the meteographs, where we do this for 15 station points in the region. What we try to highlight here is just that we report also the altitude of the point in the model, because normally the forecaster knows the true altitude of the point, of the station point, so that in case of complex orography, the forecaster knows that maybe the model in that single point is doing some underestimation or overestimation of the station height. And here you can see, okay, this is quite typical, because every 3 hours you report the forecast of the station point. We put here also the probability, which is basically of each run. It's the weight given to the products, to the individual run, depending on how the cluster was populated, which means how many members were in the cluster, which gave the initial and boundary condition. This is somehow a memory of how of the weight given to each individual run. And this is we do for Bologna, Ferrara, and several station points in the region. And here this is a similar product, but it's a sort of cumulated product, some plumes, where here you have, on the y-axis, you have the total precipitation, on the x-axis you have the day, and you have 5 lines, where the blue lines are the first percentile and 99th percentile, are the extremes, basically the ensemble. The red lines are the 25th and 75th percentiles, and the black line is the median. So in this way you can have the idea of the amount of precipitation on average by the ensemble, accumulated over a number of days, and also how much can the extreme predict over a point. And we can see, and this is again is provided over a number of station points. This is Bologna, this is Ferrara. This is quite interesting. The median is quite close to the 75th percentile over this region, which means that several members predict some precipitation over this area. Yeah. So which means that several members predict quite a large amount of precipitation on the 3rd and 4th of February this month. Okay, another plot which is, I think is quite interesting for the amount of information given is this box plot, which is again of a number of station points in terms of wind direction, wind speed, cloud cover, precipitation, and temperature. Here, okay, the spikes are the maximum and minimum of the ensemble. This is this rectangle is bounded by this 25-75 percentile, and the middle here is the medium. Interesting here is also the distribution of wind direction, which means depending on the color gives you an idea of the probability of a certain direction. For example, in this here, you have more likely wind coming from the west rather than northwest or southwest, for example, depending on the color. You can see that there is a different intensity of brown depending on the probability. And this is again given of a number of grid points which are reported over the top right part of the panel. And also the wind roses, these are all products developed by Andrea Salvini in our METOPS room. And again, this is for a particular point, which is reported here in the region, which is Bologna. You can see the forecast between day 1, day 2, day 3, day 4, and day 5. You have these isolines are probability isolines. So, isoprobabilities, something like that. And the color is the wind speed. So here we will try to summarize the prevalent wind speed and wind intensity over a point. For example, here we have between 40 at day 4, day 1, day 2, day 3, day 4, we have between 40 to 60 probabilities of having wind between 3 and 5 meters per second. While here, at day 1, I have probability about 60% of wind exceeding 5 meters per second, coming from west, from the sector. So you can see that it is quite powerful way in the sense that it tries to summarize some information about wind speed and wind intensity over a number of points. This is Bologna, again, Ferrara here, but we have, I just put two points, but we have 15 station points in the region. This is why we skip it. And this is a bit more interesting probably. We divided the region into 8 macro areas, so 8 areas which are similar size, which is about 3,000 square meters, which is about 60 grid points. In each, so A, B, C, D, F, G, H, they are the 8 macro region of Emilia-Romagna. And for each region, for each sub-region, we give the probability of exceedance of threshold in terms of error average, which means that this is the case of last week for the weather forecast for the 5th of February. You have more than 90% of probability of having more than 10 millimeters of precipitation all over the threshold for 10 and 20. Then you have high probabilities of going above 40 millimeters in threshold H, which is here. This is a plain area. This is the mountain areas. The Apennines are here. And for some areas like C, for example, the area C, which is here, the one in the Apennine part, you have probability between 70 to 90 or 50 to 70 in terms of aerial average of going above 70 millimeters. So this is quite interesting because it's called, the name in Italian is scacchiera, keyboard, which gives you just by the colors. It's very easy to probably, we think it is simple for the forecaster to have this type of message. If something is going on, you see many colors. This is for the 5th of February. For the 6th, Federico?
No, just pointing out that, and these millimeters were mainly snow, so it was a sort of 70 millimeters of snow as an average for so it was a huge, just a curiosity.
Yeah. Thank you.
And of course.
And it happened, yes, it happened. And and it is interesting because if something happening, you can see many colors which capture your eye. Then this is for the following day, where you can see some, maybe here in area G, less intensity of the event. We go up to 30 millimeter of precipitation with a probability of between 16 and 70%, and some more probabilities, some probabilities of high precipitation in area A, C, E, F. So A, C, F, over this part of the region, and then little by little the colors go down day after, and then nothing. So, which is quite, from a visual point of view, quite useful, so that it can give you some impression of what's going on, and this is quite concise in information, also useful for alert purposes. And I think that one final comment is also something that when you work on ensemble system, it's always important to know which is the use of the ensemble by the users, ensemble by the users. For example, these two meteorograms are constructed with the same numbers. But here I see the temperature, precipitation, and wind. I see the behavior of the individual members. So I can spot maybe some different, some systematic behavior or some strange differences. Here we have summarized in terms of box plot, and maybe this here nice to be seen because it's more compact. Maybe it's better for presentation to the public. This is maybe more interesting from model developer point of view because you see many lines. This is maybe it's not very nice to look, but it can be more useful to know which are the members which tends to predict large amount of precipitation. But again, it is just a way in which you can describe uncertainty in two different ways, and depends again on the use you want to make out of it. And we move now to the, I hope, something more exciting, maybe, and which is basically a part of the talk in which we try to assess the performance of the system for a number of case studies. So we look at a Swiss flood in 2005, many information provided by Andrea Valser from Meteo Suisse, again for this case. We look at the snow event and other cases, if you have time and some time to look at the question which arrived here and some tentative answers. So this is an event of August 2005 with widespread precipitation and flooding over Switzerland. The large-scale flow was characterized by, here we have the geopotential height, which are at 500 hectopascal, which are the solid black contours, while the shading is given by the temperature at 850 hectopascal, where we have this upper level cyclonic circulation with warm air, moist air, impinging over the Alps and deploying large amount of precipitation in around the 22nd of August 2005. So not very recent case study, but quite interesting to see what the different ensembles can tell you. So this is again amount of precipitation which was observed over 3 days between the 3rd and the 23rd of August 2005, and we can see peaks of observed precipitation with which locally exceeded 300 millimeters. But anyway, we can see around this central part of Switzerland areas well above 150 millimeters of precipitation between the 20th and the 23rd of August. So we can look here at this is a probability forecast of Cosmology for precipitation over 72 hours. So we can see which is the probability of precipitation over 72 hours with a forecast range between, forecast starting 18th of August, verify on the 23rd of August, with some signal of precipitation on the for precipitation exceeding 50 millimeters, exceeding 100, 150, 250. Very, very, very little signal of probabilities for high event at this forecast range, 250, 150, almost no signal. Something occurred here at the 100 millimeter threshold, and quite intense signal with probability about 80 to 90% of this lower threshold. It is interesting to compare this to the following day. This is the round starting on the 18th of August. This is the round starting 1 day later, the 19th of August, in which the signal is much clearer now. You can see higher probabilities almost all over the central part of the country for the 20, for the 50, for the remainder 150 and 250 millimeters, with some probabilities about 40% of precipitation exceeding 250 millimeters. Interesting, we try to compare what ISNWF and Cosmology were telling you. These are the same threshold, the same forecast range. We can see that Cosmology had some signal of probability above 50, 100, 150, 250, while ISNWF had very, very little signal. There is some indication of precipitation, but much more in the northeast of Switzerland, mainly in Austria, and almost no signal between 150 and 250 millimeters. So again, here, and the thresholds are the same. So we can really see some positive impact of using a high resolution system for this case study.
Andrea,
Yeah.
this is an individual case.
Yes.
And it's two probabilistic systems.
Yes.
You cannot compare them.
This is what the forecaster get in the top room. Of course you can compare.
You can look at them and see that they are different.
Yes.
It doesn't tell you anything of any value.
Yes, but we don't want to say that that's for a reason that is better, that is not better.
I think that giving two different information.
Or a decimal, that's it.
This is what the forecasters see. I don't think that in that day they will say ISNWF is always crap and Cosmology is always good. No. It's not just, this is what the forecasters see. And it may use.
But maybe that some, in other situation is the opposite.
Yeah.
That is the point.
Yeah. I'm showing case studies now.
Of course,
So-
we can show only the
not on. Yeah. So for this case, we can just see that just looking at the cosmology performance, it is a bit tricky, the thing, because you should not compare a probability with a observation, because this is in millimeters and this is probability, this is percentage. So it is just to give you an idea of the area to alert, which coincide quite well with the area where actually you had widespread precipitation and flooding. So, but this is probability, the contours are probability and the contours are millimeters. So we have to be careful in the match. So this is for the 100 millimeter threshold, and we can make a small trick to color differently. In red about 100 millimeter and in green below 100 millimeter, just to give more visually the idea of how the threshold value was giving the right area to alert. And it's interesting that the signal survive also at the high threshold. This is 100 millimeter, 250 millimeter. We can see that for this case, the guidance of the products is useful in the sense that it tells you the area to alert, which coincides with where actually then you observe a lot of precipitation for this case. So, one take-home message can be there is some added value of our resolution and some better description of holographic and mesoscale related processes for this case. So we try to give some take-home message for each case we look at. So now we look at the snow event in Emilia-Romagna, Nevone called in Italian, in Emilia-Romagna of 2012. This is quite, we will look at the behavior cosmology for this snowfall case study, which was, it is actually a period of about 2 weeks where we had several events of snowfall over the Emilia-Romagna area. This cyclonic circulation and the quite cold air, bad weather for the northeast, and then with higher snowfall over the eastern part of the region and less snowfall over the western part of the region. But I think that many of you do remember this period. This is for the, we look at this observation of the first snowfall, which occurred on the end of January. With these are observation in centimeter. We can see more, we can see higher values, 62, 65, 70 centimeter, 991 in the eastern part of the region, and 45 in Bologna, we still a lot, and lesser amount towards moving to the northwestern part of the area of the region. So more snowfall over the eastern part, less snowfall over the western part. So this is a first forecast by LAMI, the deterministic system, 3-day forecast, which was giving some forecast of millimeter of equivalent water between 20 and 50, more over this area. Scusa. Okay, so we can see here some the deterministic run of Cosmo nested on ensemble F, deterministic system, which was going for some precipitation over the southeastern tip of the region and lighter precipitation over the rest of the region. And this is the first run we will examine. Here I show for the moment the 16 Cosmolabs run, which are available just a few hours later, which was showing different weather scenarios, some with light precipitation, some of them with already a bit more. But generally speaking, we can say that there was some indication, but not particularly. And also looking, this is again what happened. And if you look at the meteogram of Bologna, this is the forecast of the 30th for the day of the second, we could see that there were some members of Cosmolabs already going for the high precipitation scenarios, heavy rainfall scenario. The black one is the deterministic run. There were many members in agreement with the deterministic run, some members already highlighting the possibility of heavy precipitation 3 days before, 12 hours, and this is what happened. This is the new run of Cosmo, 12 hours later, starting the 30th of January, 12Z, so 30 to 60 forecast range. This is the run before, which is very similar, we can see, to the previous one, almost identical. And which again goes for some precipitation over the southeastern tip and some light precipitation over the central part. And here I can see the 16 runs. Some of them are already starting to highlight in some part of the possibility of 50 to 75 millimeter of equivalent water over some parts of the region. Some of them are going for snow, almost for no precipitation. Some of them are going for heavy precipitation event. So if you look at the meteogram, we can see that deterministic run goes for large precipitation events. More and more members already tell you the possibility of a different scenario. So there is a discrepancy between the deterministic run and the ensemble runs. This is the main message. And quantitatively, we can discuss, but the ensemble seem to go for a different road. This is maybe the key message of this type for this case. If you look, this is the observation again. If you look 12 hours later again, this is the new run where the deterministic run goes for we start to have a bit more of precipitation over the southeastern part. We still some underestimation because we here in between 20 and 50 millimeters of this region of equivalent water, and 50 to 75 here, 75, 100 only on the border of the region. These are 2-day forecast range. These are the old forecast we saw before. And here we can see the different runs of Cosmolabs for the same forecast range, with some members going for, several of them by now, going for heavy precipitation event. So the range is getting shorter and shorter, and now there is a good agreement between the ensemble and the deterministic run. We can see that now the deterministic run follows the ensemble, changing its mind, which is good when a model changes its mind if it changes in the right direction. And we can see now quite a good agreement between the different ensemble members and the deterministic run. And I think this is the last slide for this case study. Now, we have also a very, very short range between 12 and 36 hours, where the high precipitation event is even more indicated by the deterministic system. These are the older runs. And again, the different ensemble members now are quite coherent. It's a quite short forecast range, so there is not much time for the different members to differentiate one from the other. And also in terms of meteograms here, where I have on the x-axis the time, on the y-axis the precipitation intensity, we can see also in terms of timing, all the members predicted precipitation, especially in the second part of the day. So what we can say by this case study is that we can try to, which is a take-home message. I don't want to make a ranking, the ensemble was better than, but the idea that it can be interesting to look at differences between deterministic and ensemble runs, just to weaken or strengthen the deterministic information. This is basically what the ensemble is designed for, to assist the forecaster, to help the forecaster to take the best decision. And in some cases, it can be interesting to look at the individual and ensemble member. It's called stamped maps. In some situation, can give some added value. In this case, was you could see some extra information. Now we can have a look at some other cases. One is quite recent, is a sea storm occurring in Cesenatico last September. There was a deep convective system of the Adriatic Sea with gale winds, which made the sea enter the town. There was no alert given, so it was not possible to set up the barriers which are present in the town to prevent this type of events. And so there was some flooding due to the sea which entered the inland. No alert was given, and this is from the report of the radar meteorological area and Sala Operativa. Here it is shown the cumulative of the amount of precipitation in the evening on the 22nd. The problem which we saw in Cesenatico is in this area, around this region. And the amount was associated with precipitation, but especially with the wind, the main problem. We can see here the amount of winds with force, for example, here we are Rimini and Ravenna. Ravenna is a bit more here, with a value of about, in the evening, of Ravenna 17, 15 to 18 meters per second, Rimini, which is just on the coast with more than 22 meters per second, and later on 21 meters per second. So maximum wind quite strong, which also occurred, and for this case study there was no alert given. And what we try to notice here is that we can try at the consistency of the signal in different runs of Cosmolab. So here I'm looking at one particular event. Probability of 3-hour gust exceeding 12 meters per second. And I look how this event is predicted for the 0Z of the 23rd of August. We can see this is a long-range forecast. Forecast started the 21st, 0Z, past 2-day forecast. We can see the probability is between, I have to look at this region, between, this is some probability of between 60 and 90% in the early, in the longer forecast range. And as the range becomes shorter and shorter, here it is around starting the 21st of September at 0, 21st September at 12, 22nd of September at 0, and 22nd of September at 12, we can see that as the forecast range becomes shorter and shorter, the signal is more and more confirmed. So this is quite a stable signal and quite coherent to some extent. So at different forecast ranges, the signals seem to be present, both at the threshold, which is 12 meters per second, and also the 20 meters per second. So between this slide and this slide, only the threshold changes on the top right part of the figure. For the 20 meters per second, we can see here that almost no signal in the longer range, but as the forecast range become more and more, become shorter and shorter, we can see some probabilities picking up. So there was some indication. I don't want to say that, this is a perfect forecast and we should do this or that. But the idea of this event is mainly maybe consider the idea of looking at probability products over short time intervals. In our weather service, we tend to look at precipitation over 24 hours, over 72 hours, or wind speed above some probability of wind speed in a day, or temperature above a maximum or a minimum in a day. Maybe we could think about considering shorter time intervals in order to pick up the development of this system, which were very fast and difficult to catch. This is what I'm just trying to put here the different take-home messages.
Andrea, if you look at shorter time intervals, the probabilities will be smaller. Generally, or always, because if you the longer the time, the higher the probability, the larger the area, the higher the probability. So by going down into smaller time, you win something, but you lose something. You have to pay for that.
Yeah, here you have all the members are quite similar, and they all go for similar scenarios, and the probabilities here are quite high for all this local area. Yeah, for this case study, you can say that there is not much, there is quite agreement between all the different runs, and you get high probabilities. Yeah, I agree with depending on the area you are considering, but
It's a mathematical.
yeah. These are the products the forecaster can have. Again, here we can have a look quickly at some new products which are typically available with new convection resolving ensembles, which are ensembles with high resolution without parameterization of convection, so convection permitting ensemble, which are developed in Europe. There are at the moment in France, over UK, and in Germany. That this system, only one is operational. It is Cosmology EPS, which uses 20 members, 2.8 horizontal resolution, 20-hour forecast range, and it is run 8 times a day. So every 3 hours, they have this high resolution ensemble running at DVD. So we can try to see how this system can help in the prediction of extreme events. And of course, the system, due to computation time, they can run only over a small domain. Morgas UK run only over this small area. Cosmology EPS runs over this domain here, which covers Germany, but not Italy, for example. And while the around France is the one with the largest domain. But now we concentrate only on Cosmology. And we can see a case study of 18th of June